Hello everyone. In this video we will be talking about how to solve trigonometric integrals. So what do we mean by trigonometric integrals? Well, we are going to look at integrals of the form sine to the m of x cosine to the n of x dx, where m and n are both non-negative integers. Okay, so different powers of sine and cosine so long as these powers are non-negative. And basically, these can be broken down into two cases. So the first, which is the easier one, is where at least one, of m and n are odd. And then the second case, which requires a little bit more work, is where both m and n are even. So first, let's take a look at when at least one of m and n is odd. So let's first take an example where you could already do it without any new method, right? So if we look at this integral here, then we can see that, okay, this looks like an inside function, right? Cosine is being raised to the fourth power. Its derivative involves sine. And so we would think this is actually just kind of a straightforward u sub, right? So u is cosine, du is negative sine. And so we end up getting the integral of, okay, so we have a negative sign, but it's just u to the fourth du. And so we get negative 1/5 u to the fifth. And replacing u, we get negative 1/5 cosine to the fifth x plus c. Okay, not too bad. So now what if I replace that power of sine, and instead of just one sine, I have three. So I have cosine to the fourth and sine cubed. So the issue here, right, is that u substitution doesn't really work out because both of them seem to serve as inside functions. So can we reduce it in some way to the previous case, right? And so here's where having an odd power of 1 is important, right? So sine has an odd power to the third power there. And so last example, right, we just had sine x. So can we get it there? So can we pull out a sine squared and do something useful with it? So let's pull it out first. So if we can somehow put this in terms of cosine, right, then the sine x kind of fits into our du and we can do a u substitution again. And remember, we have the Pythagorean identity, right? So that is sine squared plus cosine squared is equal to 1. And so in this case, we can always replace sine squared with 1 minus cosine squared. And so when we actually do this out, right, we're going to get cosine to the fourth times 1 minus cosine squared. And so when we distribute this guy, we get everything here in terms of cosine with this one power of sine left over that allows us to still do u substitution, right? So now we're ready for the u sub. And it follows just like it did last time, right? So u is cosine again. It's just a little bit longer this time. And du is, again, negative sine x dx. And so now we have integral of, or I guess negative the integral of u to the fourth minus u to the sixth du. And so when we do this out, right, we're going to get u to the seventh, or cosine to the seventh x over 7, right? Negative negative is positive there, minus cosine to the fifth over 5 plus c. So the key here, right, was the fact that this power was odd, because every time we use the Pythagorean identity over here, we can reduce powers by 2. And so if you have an odd power and you keep reducing by 2, you can eventually get down to 1, which allows you to do a u substitution. So now for your first exercise, I want you to go ahead and evaluate this indefinite integral where, again, one of the powers is odd. So the next case we want to examine is if both powers of sine and cosine are even, right? So here we will want to remember a few trig identities. They're going to be helpful for us. Basically, we want some way, right? Because the issue, why we can't do the same thing as last time, right, is that if you just keep reducing by 2, you're never going to hit the power 1, right? And so you can't do this nice u substitution as before. So is there some way that we can reduce an even power to an odd power, right? Can we reduce the power by 1? And so one can do this via the half angle formulas. So let's remember these. So cosine squared x can be rewritten as 1 plus cosine of 2x over 2. Sine squared x is the same thing, except for it's a minus instead of a plus, right? So we've reduced the power from 2 to 1. And then this last one is a double angle formula for sine. And so this is that sine x times cosine x is equal to 1/2 times the sine of 2x. So these three formulas will be useful. So let's just take an example and see how it goes. So a somewhat simple looking integral that we actually have not yet done is just cosine squared, right? So in this case, again, we only required these were non-negative integers, so 0 is perfectly fine. And so this is sine to the 0th power, whereas cosine is squared, and 0, of course, is even. So this falls under this case. So, right, we can't just do this on its own, right? We can't let u be cosine because there is no sine involved. So there's no way to get the du here. And so we would like to reduce the power by 1 so that we can deal with, just cosine. So how do we do that? Well, like we just saw in the last one, cosine squared is 1 plus cosine of 2x over 2, right? Using this half angle formula. Well, now let's take a look at this. So once we have just a single power, this isn't too bad, right? So we can split the numerator here and view this even as two integrals. And so this is cosine of 2x over 2. So the one on the left is quite easy, right? So this is just 1/2 x. And this one over here, well, we're doing like a very slight substitution, right? Where 2x is our inside function. And you could also probably just eyeball this one and see that it is 1/4 sine of 2x. We know it has to be sine to get cosine. And 1/4 is the right thing because the chain rule is going to have us multiply by 2, and we want to end up with a 1/2. And so this works out very, very quickly. So for your second exercise, I want you to go ahead and just add a little bit of complexity there. So go ahead and look at sine squared times cosine squared and do that integral. All right, thank you for watching.